let's see for the first order reaction. First order reaction, that is order is equal to 1. Generally, what is first order reaction? Then simply I will say it is a reaction in which the rate of a reaction depends on single reactant and with the power 1, that also raised to power 1. For example, suppose I am saying A is giving product. A is giving product. So here I can say if it is a first order reaction, then I can say that rate is equal to K into molar concentration of A raised to 1, that is. So let this is equation number 1. So here I can say rate is directly proportional to the concentration of only one reactant, that is A, and that too raised to power 1. Now let us derive an equation again, formula for the first order reaction also, that is integrated rate law formula. So rate is equal to K into molar concentration of A. Similarly, I can write the instantaneous rate. So instantaneous rate is equal to minus, only in terms of reactant, that is minus dA by dt. Equation number 2. Both gives the formula for rate, so they are equal to each other. So I can say that from equation 1 and 2, minus dA by dt is equal to K into molar concentration of A, I can write. Let us take A here, so we will get dA upon A is equal to minus sign into K into and dt on this side. So we got this. Again, the next step is integration, because these are the small changes, that is a differential form, that is a small changes, and I want the formula for the full reaction. So for full reaction, so we have to remove this differential form, that is integrating, which can be done by integration. So integration of dA upon A is equal to integration of this minus K is a constant, and then dt. Again, the definite integration, that is means again we are fixing a limit for it. The lower limit for the concentration is A naught, to the upper limit is AT. For time it is 0 to T. Now, it is an integration of 1 upon A. 1 upon A integration is 1 upon x integration is ln log x. So similarly, if it is a 1 upon A, then integration is going to be 1 log A. Here it is a natural log, that is a log to the base e. So instead of log to the base e, we just write ln. So it is ln A. The lower limit is A naught and the upper limit is AT. What is ln? As I said, when we write the integration of 1 upon A, it is a log A, but that log is log to the base e. That is a natural log or exponential log, I can say. So instead of writing full log e, we just write ln. So it's a log to the base e A, and this is equal to minus K into dt. Dt, the integration is going to be T, and this is 0 to T. So here I can say, right, ln AT minus ln A0 is equal to minus K in bracket T minus 0. That is again upper limit minus lower limit. It is in a log and subtraction. So instead of subtraction, we can write it in the division form also. That is AT upon A0 is equal to minus K. T minus 0 is T. Let's shift minus sign on the left hand side. So it will become ln AT upon A0 is equal to K into T. Multiply minus sign with this. So if I am multiplying minus sign with this, it will get we will get the reciprocal of it. So it will become from AT upon 0, it will become A0 upon AT is equal to K into T. I want the formula for K. So for the formula of K, it will be we will have K is equal to 1 upon T ln A naught upon AT. Okay, so we have here the formula in terms of exponential log. If I wanted to convert into the log to the base 10, then we have a relation. If you want to convert ln into log to the base 10, that is log to the e to the log to the base 10, then multiply it by 2.303. So instead of ln, I can write log to the base 10 as a 2.303 into log to the base 10. So I just wanted to remove ln from here. So we will have k is equal to 2.303 upon t log to the base 10 a naught upon at. So this is we have a formula for k for the first order reaction. Before this, we derive a formula for k for the zero order reaction, and the formula was k is equal to a0 minus at upon t, and here we have some different formula for k. It is 2.303 upon t log to the base 10 a naught upon at, and this formula is applicable only when the reaction is first order reaction. Now we can write the different form for this reaction. Suppose now what is A naught here? The A naught is again the same when it is a concentration of reactant like the previous one. The concentration of reactant when the time is 0, and AT is about concentration of reactant left after time t. So now let's see the another form for the first order reaction. So let A, small a, it is the initial concentration of reactant, and X, it is a concentration of reactant consumed in time t. So we got A and X, and I wanted to write the same formula in terms of small a and X, where A is the initial concentration of reactant and X is the concentration of reactant which is consumed in time t. So here I can say A naught and AT we are having. So A naught, which is the initial concentration. So A naught will be replaced by small letter a, that is the initial concentration. What is AT in this case? AT is the concentration which is left after time t. So initially amount taken was A, out of which X is a consumed. So left amount is A minus X. So instead of this A naught and AT, we can write here K is equal to 2.303 upon T log to the base 10. Instead of A naught, now we have small letter a upon A minus X. This is the formula. K is equal to 2.303 upon T log to the base 10 A naught minus A upon A minus X, where A is the initial concentration and X is a concentration left after time T. Now, since in the formula we are having ln, so we can write the same formula in terms of exponential form also. This is equation number 3. So let us write the same first order formula in exponential form. So in exponential, for writing in an exponential form, I'm considering equation 3. So from equation 3 we have ln AT upon A0 is equal to minus KT. There is a ln, let us remove ln. So ln is nothing but the log to the base e. So taking antilog on both sides. So if I am taking antilog, it will become AT upon A0 is equal to, here it will become antilog of minus KT. So instead of writing antilog, I can write small letter e, that is exponential raised to, and we are calculating that we want the antilog of minus KT. So the term whose antilog is to be taken is always written to the power of e. So it is going to be minus KT on the power of e. So here I can write AT is equal to A0 into e raised to minus KT. This is the third form for the first order reaction. So ultimately we are having three different forms for the first order reaction. This is the first, second, and this is the third one. This is in the terms of initial and the left amount. This is in terms of the initial amount and the amount which is consumed, that is X, and this is the exponential form, and this exponential form formula is sometime asked in MCQs. So this is about the first order reaction. We derive a formula for the first order reaction, that is the formula for the K. The formula is 2.303 upon T log to the base 10 A naught upon AT, where A naught is the initial concentration and AT is a concentration after time T. And another case, we have a formula log to the base 10 A upon A minus X. And in the exponential form, we derive a formula that AT is equal to A0 into e raised to minus KT. The next is the half-life period for the first order reaction. We did half-life period for the zero order reaction, in which we got a formula T half is equal to A0 upon 2K. Now the next is a half-life period for the first order reaction. Now again, the half-life period means the time required for the reactant concentration to reduce to half of its initial amount. So when I'm talking about the half-life period for this, so for first order reaction, we have a formula for K. That formula is K is equal to 2.303 upon T log to the base 10 A naught upon AT. Now suppose one half-life period is completed. So after a half-life period, one half-life period is completed. That is, I can say T is equal to T half. And after one half-life, if the T is equal to T half, then how much reactant will be left? Then it is A left reactant, that is AT. It is going to be the half of initial amount, that is A naught upon 2. So here I can say that K is equal to 2.303. Instead of T, I can write T half now, and log to the base 10 A naught upon, since it is a half-life period now, so it's a A naught AT. Instead of AT, I can substitute this formula, or this value, sorry, A naught upon 2. A naught will get cancelled. Ultimately 2 will get to the numerator. So we will have K is equal to 2.303 upon T half log to the base 10 2, which can also be written as K is equal to 2.303 upon T into log of 2 is 0.3010 upon T half. So we will have a formula for T half, that T half is equal to this into this will give you 0.693. So 0.693 upon K. So we get this formula. From this formula, one important thing I can say that in the formula there is a no initial concentration, that is the formula does not involve A naught. In zero order reaction, the formula was having, the half-life formula was having A naught. But here there is a no A naught. So here I can say half-life period of first order reaction is independent of initial concentration. It is independent of initial concentration. Okay. So this is again a very important statement, that there is a no dependent, means you take small amount of reactant or large amount of reactant, the half-life period is going to be same. For example, it means if I am starting with 100 gram of reactant or 100 molar concentration, suppose after 30 minutes this concentration reduces to 50 molar, means this 30 minute is going to be the half-life period, that means. So instead of 100 molar, if I am starting with let 200 molar, that means the initial amount has been increased, but still the half-life period is going to be same, that is 200 molar will get converted into 100 molar only after 30 minutes. So half-life period does not depend upon the initial concentration. Now if I'm starting with if I'm talking about the half-life period, let's see how many half-life period will be needed to complete the total reaction. So if I'm taking 100 gram of 100 molar reactant, after a half-life period, after next half-life period, it will be, now in zero order reaction, from 100 it was 50 and from 50 it was 0. But in case of first order reaction, after next half-life period, it is going to be a 25 molar. That means again it will reduce to half amount. The amount is not going to be 0, because in case of first order reaction, the rate of reaction depends on the concentration of reactant. Depends on concentration of reactant, it means if during the process the reactant has reduced, and if the reactant has reduced, then rate of reaction has also decreases. So if the half-life period is 30 minutes, suppose, then in first 30 minutes the reactant reduced by 50 gram or 50 molar. So in next 30 minutes the reactant will be reduced only by 25 molar, because the reaction speed has also decreases. In next half-life period, this value reduces to 12.5 molar. Now let's talk about, so this is the half-life period for the zero order reaction. Now let's talk about the total life period. So for total life period, again I will start with the same formula. K is equal to 2.303 upon T, or instead of this, let's start with another one, that is AT is equal to A naught into e raised to minus KT. Now, if the time is after T is equal to total lifetime, that is LT, then AT will be equal to total lifetime means, I'm talking about the total lifetime means all the reactant has been consumed. So a reaction is completed. That means there is no reactant is left. AT is equal to 0. So AT is equal to 0. So from this I can say 0 is equal to A naught into e raised to minus KT. Now from this formula, A naught should not be 0, because initial amount of reactant will not be 0. So I can say this is 0 because of e raised to minus KT. So e raised to minus KT is equal to 0. Again I can say K, this is T is total lifetime. Again, the K is a rate constant. So being a rate constant, it's a constant. So again it cannot be 0. So I can say I'm getting the e raised to minus KT 0 only because this lifetime, that is time. So what will be the value of time so that it will give you the 0 value, then I will say that here the time value will be infinity, then only you will get e raised to minus KT as a 0. So here the total lifetime of a first order reaction is infinity, means we cannot decide when the reaction is going to be completed. And ultimately from here also you can see that 12.5, then next half-life it will become 6.25, then 3.125, then 1.5 something. So it goes on continuously. So getting total lifetime for a first order reaction is difficult, means here it cannot be predicted as we predicted in case of zero order reaction. So keep in mind, total lifetime for a first order reaction is infinity. The next is the graph for the first order reaction. Like a zero order, we have a graph of first order also. So graph of first order. Again, by the graph, from the nature of the graph, we can say whether the reaction is a first order or not. So we have the certain graph for this. The first one is the graph of rate versus AT, that is concentration of reactant. Now let's see what will be the nature of the graph of rate versus AT. So for the first order reaction, we know that rate of reaction depends upon the concentration of reactant. And we have relation that rate is equal to K into molar concentration of A. Instead of A, I can write AT also. First order is, so the power is going to be 1. So rate is directly proportional. Directly proportional means the graph is going to be linear and passing through origin, or so it's a directly predictable. Or I can say if I'm comparing with the same y is equal to mx plus c, then I can say on y-axis we have rate, on x-axis we are having concentration of reactant, time is going to be slope, and the c is going to be 0. C is a 0, that is a y-intercept 0. Y-intercept 0 means the line is passing through origin. Slope is positive, it means from down to top, and slope is k here. So if I'm plotting a graph, so rate versus concentration of reactant, that is AT. Then the graph is a straight line passing through origin, means the nature of graph is something like this. And when we calculate slope, the value of slope is equivalent to the value of k, means from the slope we will have the value of rate constant, that is k. Then second is a graph of AT versus time. AT, it means the concentration of reactant versus time. Now again, to know the nature of the graph, better to think about that which equation or which formula have both AT and time. So we have only one formula where AT and times come together, and the formula is AT is equal to A0 into e raised to minus kt. There are various formula in which we are having AT, but we do not have AT singly, but it is in the form of log AT. I want only AT, so there is only one formula, there is AT and there is a T. Since both are related to each other by the exponential equation or exponential formula, so the nature of graph is going to be indirectly curve shape, because the exponential graphs are always curve shape. So this is AT versus time. You have to just decide the nature of a graph, the graph curve, whether it will be from top to bottom or bottom to top. And then ultimately simply I will say when the time is very small, the amount of reactant left is very large. As the time increases, the amount of reactant goes on decreasing. Means the curve will be something like this. So this is the nature of graph. Then third one is a graph of log to the base 10 AT versus time. Now log to the base 10 versus time. Now we have this equation, or these two are related by a formula of k, that is k is equal to 2.303 upon t log to the base 10 a naught upon at. So we have formula k is equal to 2.303 upon t log to the base 10 a naught upon at. As I said, that try to convert the formula in the form of y is equal to mx plus c. Let's see. So try to convert it into the y is equal to mx plus c, where the y will be on the left hand side, x will be on the right hand side. Matlab y and x terms are going to be on the opposite side. Here we have this as a y and this is going to be a x. So this is y and this is x. So shift t on the left hand side, so it will become k upon 2.303 into t, and log this at. It can be written as log to the base 10 a naught minus at. Again at, which is on y-axis, which is going to be on a y-axis, a negative, so make it positive by shifting on the left hand side. So we will have log to the base 10 at is equal to log to the base 10 a naught minus k upon 2.303 into t. So now we got equation y is equal to c plus mx, or I can say y is equal to mx plus c. So comparing with y is equal to mx plus c, we will have this is on y-axis, decided. So this is x is already, it's a time. So m, it is going to be minus k upon 2.303. This minus will be considered with the k upon 2.303, not with the time. And the c, that is the y-intercept, is going to be log to the base 10 a naught. So here, the nature of a graph. It is log to the base 10 at versus time, that is t. The graph is going to be a straight line because it is like a y, it is in the form of y is equal to mx plus c, but slope is a negative here, so the graph is going to be from bottom to top. So, and it will cut y-axis also because we are having y-intercept. So the graph nature will be something like this. The point where the graph is intersecting y-axis is log to the base 10, will give you the value of log to the base 10 a naught if I'm calculating its slope, the slope is going to be minus k upon 2.303. That is, the slope is negative. So we have this third graph for the first order. Now the fourth, that is a graph of log to the base 10 a naught upon 80 versus time. Again, these two are present in a same formula, that is k is equal to 2.303 upon t. So we have a formula which relate both the term, that is k upon 2.303 log to the base 10 a naught upon 80. Again, try to convert this whole formula in the format of y is equal to mx plus c. Now this is going to be on y-axis and this is on x-axis. So shift t on the left hand side. So we'll have k upon 2.303 into t is equal to log to the base 10 a naught upon 80. This is y-axis. So comparing with, I can say y, this is on y, is equal to mx plus c. This is on x-axis, this is the slope, and the c is 0. So here we will have a graph of log to the base 10 a naught upon 80 versus time. The nature of a graph, it is going to be again a straight line. Y-intercept c is equal to 0. It means the line is passing through origin. So this is the nature of graph. The slope is equal to here, k upon 2.303. In this equation, the slope is minus k upon 2.303, while in this case, slope is equal to slope is equal to k upon 2.303. Means by making a small changes, we can find out the values of slope as well as the y-intercept. And in the exam, they ask like a question, like if the graph of log to the base 10 80 versus time is plotted, then the slope of the equation is going to be. The answers will be minus k upon 2.303, k upon 2.303, 2.303 upon k or k. So you have to select the correct answer. So these are the four graphs we are having for the first order reaction. When we plotted the same graph for the zero order reaction, that it was a straight line. So if I'm getting a straight line for the rate versus 80, the reaction is going to be a zero order. But if I'm getting a graph like this, I will say the reaction is first order. When we plotted this graph for the zero order reaction, again we get a straight line. Well, in this case, we are getting a curve. So if it is a curve shape, it is going to be a first order reaction. And if it is a straight line, it is going to be a zero order reaction with a negative slope.